Okay, so welcome Dylan Peifer from Cornell. So he'll speak on improving Grosvenor basis computation.
Yeah, so hello everyone, good to see you. Thank you for the invitation here today. This is actually, I think, the first time I've been invited somewhere to speak about my work, so I'm very excited about it. What I have for you today is a talk I've titled Learning Selection Strategies in Buchberger's Algebra, but as you said, it's kind of about how you would apply reinforcement learning to improving Grosvenor basis computation. Now, I am a 6th year, hopefully final year, PhD student at Cornell. I work with Mike Stillman. I do a lot of Grosvenor basis stuff. I'm very interested in how to compute Grosvenor bases quickly. But this project actually started about 2 years ago. The main idea actually came from Dan Halpern-Meissner, who is, or at the time was, a new professor at Cornell. And he had been reading about AlphaGo, which was a very exciting thing in 2017. AlphaGo was a computer agent that had been trained to play Go better than any human could play it. And he saw in the AlphaGo paper and in the reinforcement learning background kind of an idea for how to improve Grosvenor basis computation. He saw kind of something that looked kind of like Buchberger's algorithm, that looked like we might be able to use reinforcement learning methods to improve Buchberger's algorithm. And so that's what we've been working on, the three of us, for the past 2 years, through lots of failures and a couple of successes. And so I'm going to tell you a little bit about the successes today. So if you get one thing out of this talk, I think it's just these two sentences at the start, just an overall outline. So the efficiency of Buchberger's algorithm strongly depends on a choice of selection strategy. There's a heuristic inside Buchberger's algorithm that any implementation has to deal with, and that can actually make huge differences in how fast that implementation is in computing a Grosvenor basis. By phrasing Buchberger's algorithm as a reinforcement learning problem and applying just standard reinforcement learning techniques that are well known and at least reasonably well understood, we can learn new selection strategies.
Pre-selection, which S polynomials you choose, or
which S polynomial, yeah, which S pairs to reduce. So we can learn new selection strategies that can match or beat the existing state of the art. So this is a talk in 3 parts. The first part, I just want to tell you what a Grosvenor basis is and what Buchberger's algorithm is. I don't know, what are people's backgrounds? Does everyone know what a Grosvenor basis is? Could you define it right now?
So more than half, I think, know what Grosvenor basis is.
Okay, we can go through that a little bit fast. I mean, could you write down Buchberger's algorithm? Could you tell me what a selection strategy is?
About half, maybe.
About half. Okay, we'll go through it fast. Let me know if I'm going too slow or if I'm going too fast on that section. The second part, completely independent from the first, I want to tell you about reinforcement learning and policy gradient. So it's very important what it is that reinforcement learning is actually trying to solve. And policy gradient is one method to solve a reinforcement learning problem. I imagine you have less experience with this, yes?
Yes.
Yeah, so we'll go a little slower in there. And then, still some? Yeah.
Some people.
Okay, so then we will take these two completely different things, parts 1 and 2, we're going to shove them together, and we're going to see what happens when we apply reinforcement learning to Grosvenor basis computation. Anyway, let's start with Grosvenor bases. Just a standard introduction. Let me know if I'm going a little too slow. So, standard setup of commutative algebra, we are in a polynomial ring over some field K. Don't care what the field is. My favorite fields tend to be finite fields with large characteristics, but you can put whatever you want right there. And we're looking at ideals generated by polynomials in this ring. So a quick example, just take polynomials in xy with rational coefficients, that's q with x and y in it. And here's an ideal, x squared minus y cubed, xy squared plus x. And of course what that ideal is it's everything that looks like a multiple of x squared minus y cubed plus a multiple of xy squared plus x. So, with this very basic example, I have a question for you. In this example, in this ideal, is x to the 5th plus x an element of I? Is it an element of the ideal? Anybody got a guess? I mean, some of you already know how to do this, but if you don't know how to do this, yes, no, maybe. Maybe. I think this example is supposed to be hard to tell just by looking at it, so I don't think you can tell immediately. This question is actually, I mean, it's not super hard, but it is surprisingly hard. I think I first saw a question like this when I was like a 2nd year grad student, first reading about computer algebra, and I was surprised by how difficult it was. I thought I knew what ideals were, right? I had taken several courses in abstract algebra. I had done all sorts of proofs about modules and that kind of nonsense, but I couldn't answer this question in a very general, precise way.
I think it's not in there.
You think no? Why not?
Because if you want to use the second polynomial to kill the y, then you have to
Yeah, you're gonna have to kill that y cubed. If you ever
Yeah, that's
use,
right. You're gonna kill that y
if you want to
cubed.
get the x squared, maybe by multiplying by x cubed, you're gonna have to kill an x cubed y cubed. But you could do that by multiplying the second thing by x squared. But then you introduce another x cubed.
Right. It seems like
You need to get rid of that.
Yeah.
Maybe.
Yeah, that's
We'll
mentally.
see.
That's how I would guess. Yeah.
Right. So, standard problem solving strategy. When you have a question you can't solve, make the question easier. See if you can solve that, and then generalize upward. So, in the land of polynomial rings, there's two ways to make our life easy. One way is to say that all our polynomials are actually linear. In this case, we're just doing linear algebra, and linear algebra is the most unreasonably overpowered field of mathematics I've ever seen in my life. And there is a version of this talk that goes through linear algebra, that starts with row reduction and gives you Grosvenor bases. But I like the other version of the talk, which is the one I'm giving you, which says the other way to make our lives easy in a polynomial ring is to think in just one variable. So let's take this polynomial ring. Let's not think in two variables. Let's give ourselves a question in one variable. So in just qx, just one variable x, here's an ideal, x squared plus x minus 2, and here's an element, x cubed plus 3x squared plus 5x plus 4. Now can we answer this question? This hopefully should be easier, and it should bring up memories of, I don't know, middle school, high school, kindergarten, whenever you learned about polynomials and long division and whatever. This is just long division. We need to check, is x cubed plus 3x squared plus 5x plus 4 a multiple of x squared plus x minus 2? And I know how to check that. I just do the long division. I write down here in blue, x cubed plus 3x squared plus 5x plus 4. That's the dividend, I guess. Is that the name we call that thing? Never
But you
remember.
don't even have to do this. You just plug in 1 into the.
You could do like a faster, like.
But then it vanishes. The generator doesn't vanish this.
So you're being more clever. I could give you other polynomials where that would not work as well, but I appreciate the cleverness. That's a good point here for this example. Anyway, if you're not quite as clever, you do this division. So you take x squared plus x minus 2, you divide it in. The way you do that is you look at the lead term, x squared, you subtract off a suitable copy from x cubed, and so on and so forth. You get out a non-zero remainder of 5x plus 8. This tells you, of course, that the blue thing, x cubed plus 3x squared plus 5x plus 4, is this multiple of the orange thing plus a non-zero thing, which means it's not a multiple of x squared plus x minus 2. And we now know that it's not in the ideal. Okay, great. So how do we generalize this upward? It worked right here in this univariate case. What about multivariate polynomials? How could I do long division if I have multiple variables? Seems like you could probably still do it, right? But the first thing you run into when you start thinking about it is kind of important that I could look at that and say x squared is the lead term of the orange thing and x cubed is the lead term of the blue thing, right? But now what is the lead term when you have multiple variables? I've got like x squared y and I've got a yx squared. Which one of those is bigger? I don't know. So really the solution is just to choose. So here I have x to the alpha is an arbitrary monomial. So alpha is, say, the vector of exponents. The first component is the exponent on x1, the second component is exponent on x2, and so on. A monomial order is just going to be a relation on monomials. And it's going to have to satisfy a couple properties. The first is that it's a total order. This is just so I can look at any polynomial and I can put it in a unique decreasing order, put its terms in unique decreasing order. Second is it actually has to be a well order. This is so the division algorithm will terminate. The wonderful thing about the division algorithm is that every step strictly decreases the lead term. And as long as I can't strictly decrease forever, which is exactly what well ordering says, I know that the division algorithm will actually terminate. And finally, this thing will respect multiplication, which means if two monomials start out one bigger than the other, and I multiply by anything, they stay in that same order, which is useful whenever I multiply things that they don't just start shuffling around.
Is this okay for those who never seen this before? Can you follow?
Yeah, good? So a standard order that you might come up with the first time you saw this is Lex order. Lex order in kind of complicated notation says that x to the alpha plus x to the beta, x to the alpha is greater than x to the beta if the leftmost non-zero component of alpha minus beta is positive. The way to actually think about this is that you're just ordering the monomials as you would alphabetically. So starting from the left and going to the right, you see which monomial has more x's. Then you see which monomial has more y's if you have to break ties. And then if you have to break ties further, you see which monomial has more z's. So it's just the order you would see these monomials in the dictionary. Now there are lots of other orders. For the purposes of this talk, Lex is perfectly fine to think about, but all of the computations I'm going to show you after we get through this section are going to be done in Grevlex, because that's typically considered a better order to do Grosvenor basis computations in. So let's apply our wonderful new technique. So we take...
Do you have a sort of justification for that general belief?
For why Grevlex?
Grevlex is best.
I had exactly the same question.
So why is Grevlex better?
I know in the 80s when
They all say that.
still learning also. Yeah.
So there are bounds on regularity that are tighter in Grevlex than any other order that you can prove.
Okay.
This is actually a paper I can point you to. It's actually a paper of my advisor, which I should have read at this point, but I've never actually read.
Right.
But this is, I mean, yeah, I don't think it's a actually great justification for why Grevlex is better. There is lots of kind of practical justification. When you do these problems, it tends to be the case that Grevlex works better. But no, I mean, it's not even entirely clear that Grevlex is the obvious choice here. It's just typically used in practice. Anyway, we're doing this Lex order. We're dividing fifth plus x by these two generators. Now, in multivariate polynomial long division, I can have multiple divisors. All that means is I have to keep track of multiple quotients. There's no real exciting difference here. So at any step, I'm going to subtract off, just like I did before, a multiple using the lead terms. And since I have multiple divisors, sometimes I have choice, sometimes I can pick one or the other. I just have to keep track of which one I'm dividing by at which time. So if you do this, you can check my math. I think you actually get out 0. Somewhat surprisingly, maybe. Which tells you that x to the fifth plus x is a multiple of the first generator plus a multiple of the second generator plus 0. In other words, it is in fact an element of the ideal. Hard to tell, but we can actually do it. You were, yeah. I mean, it's hard to tell. I think when I looked at that, I didn't think it was. Especially since it's like only in x's. It seems hard to deal with the y's somehow.
And is this the smallest degree in x polynomial that only depends on x's and the ideal?
I have no idea. Maybe?
Probably.
Probably? I mean, 5 is pretty small. Could you get a 4 in there somehow?
Imagine worse.
I don't know.
Things.
Okay.
You could play around with it using Macaulay too. Anyway, we have now solved our problem, right? So we say when f is a set of polynomials and dividing h by these f's using our new multivariate polynomial long division algorithm, if it gets to remainder r, we say that h to the f goes to r, or h reduces to r. This is a reduction algorithm getting out a remainder. And, of course, you could all prove right now that if h reduces to 0, then h is in the ideal generated by f, because the multivariate polynomial long division algorithm just gave me a way to express h in terms of the divisors, in terms of the generators. So, this seems done, right? We solved it. But if you're being very, very careful mathematician, you notice that this is only one direction. This says, if h reduces to 0, then h is in the ideal generated by f. But I really want that to be an equivalence, right? I would really like it to be the case that if something was in f, or the ideal generated by f, then doing multivariate polynomial long division would lead to 0. And it seems like that should be the case, right? In any sane world, that would be the case. You're unconvinced. Maybe you know the answer, because the answer here is that the converse is actually false. It is not true in general that elements in the ideal generated by f have to reduce to 0 when applying the multivariate polynomial long division algorithm. Here's a quick example. This is the same ideal we saw before. Here, I have explicitly constructed for you an element in I, right? I told you how to make it. Do y squared times the first generator minus x times the second. That thing, minus x squared minus y to the fifth, well, it's definitely an I, but if you apply multivariate polynomial long division, I think you're first going to cancel the x squared with x squared minus y cubed. You'll get out negative y to the fifth minus y cubed. You no longer will be able to do any division steps, and that thing's not 0. So, at this point, we were very unhappy. Right? This is very unfortunate. We had a great idea and it didn't quite work. So how do we solve this?
But you see that y cubed is actually x squared.
Y cubed is x squared, yes.
So I replace y cubed by x squared.
And then you're back where you started, negative x squared minus y to the fifth.
Oh, that's where I started.
Now it is true you could mess with the monomial order here, but you're not really allowed to do that.
I know.
You have to pick some particular monomial order.
I'm just trying to look through.
Yeah.
Just trying to hack it.
It's trying to figure it out here, yeah. Anyway, I'm going to solve this problem by essentially defining it out of existence. I'm going to define now a Grosvenor basis for you. So given a particular monomial order, a Grosvenor basis of an ideal is going to be a set of generators such that what I want to happen actually does happen. So I can write this down in three equivalent ways. The first way is kind of what we've been talking about. A Grosvenor basis has the property that dividing something with multivariate polynomial long division leads to 0 if and only if that thing is in the ideal. So the forward direction is obvious, that always happens, but it's the reverse direction that's really giving us this definition of a new interesting object of Grosvenor basis. There's other ways to write this down equivalently. This multivariate polynomial long division gives unique results. This, I think, is what people really cared about when they first were studying Grosvenor bases. And you can also write this down in terms of the lead terms. So the lead terms of the generators generate a monomial ideal that is, in fact, the monomial ideal generated by the lead term of I, which is the set of all lead terms of polynomials in I. So we have an example now, at least of something that's not a Grosvenor basis. This thing we were just looking at, x squared minus y cubed, xy squared plus x, is not a Grosvenor basis of the ideal because it didn't work for doing this polynomial long division. But that's not very helpful.
Wait,
What?
we didn't check that this is the case for all monomial orders.
So Grosvenor basis is for a fixed monomial order.
That's right. That's right.
So the Grosvenor basis,
Given a monomial order.
Yeah, that's right. So you say it's not a Grosvenor basis. So you're implying that you're.
well, it's not a Grosvenor basis in Lex.
Lex.
Right.
Lex. Okay.
Yeah. So we are for these examples we're staying in Lex, just because it's kind of the most familiar and the most easy, I think, for people to do it first. So yes, more precisely, this is not a Grosvenor basis of I in Lex order.
Right.
But what is a Grosvenor basis? Can I even find one? Does it even exist? Well, to take a look at this, I'm going to define for you an S polynomial. Here, S stands for subtraction or syzygy, depending on who you are. I like the word syzygy, so I say syzygy all the time. I don't know if anyone else has preferences. This S polynomial has a definition of x to the gamma over the lead term of f times f minus x to the gamma over the lead term of g times g, where x to the gamma is the LCM of the leading monomials of f and g. This is kind of a painful looking definition at first, but what's happening here is that you're multiplying f by a monomial and multiplying g by a monomial such that the two leading terms are now the same. And then you're subtracting the two, which is going to cancel that leading term. So you've already seen an example of one of these, the thing I showed you that broke our attempt at finding the Grosvenor basis. If I take x squared minus y cubed and xy squared plus x, I can produce the S polynomial. Notice that x squared and xy squared, their LCM is x squared y squared. So if I want to get a lead term of x squared y squared on the first, I need to multiply by y squared. If I want a lead term of x squared y squared on the second, I multiply by x. Then I subtract to cancel that lead term, and I'm left with negative x squared minus y to the fifth, which is the thing we saw before. So this certainly seems like S polynomials are good things to notice problems in a particular generating set. That Grosvenor bases depend upon divisibility of lead terms, and doing this weird cancellation of lead terms might kind of reveal new behavior that we'd have to handle in terms of actually having Grosvenor bases. But the sort of surprising thing is that the S polynomials actually cover all of the bad things that could happen. And so Buchberger's criterion, which is kind of the main contribution of his 1965 thesis, is that a set of generators of an ideal, let's call them G1 through GS, this set is a Grosvenor basis if the S pairs of the set, the S polynomials between all of the elements in the set, reduce to 0 when divided by that same set. That is, in fact, a Grosvenor basis. So it's initially a little bit surprising. I think that S polynomials are all that you have to care about when computing a Grosvenor basis. The way that you would actually prove this is show that if you have an element in the ideal, that element is certainly a sum of multiples of the generators, right? Which means it's a sum of things that are certainly divisible by the generators, right? So the only thing that could go wrong is some complex cancellation in the sum of the lead terms. And all you have to show to prove Buchberger's criterion is that complicated cancellations can be expressed in terms of these simple S polynomial cancellations that are cancellations pairwise in kind of the simplest possible way. Anyway, the wonderful thing about Buchberger's criterion is this is something we can actually check. And it leads to then Buchberger's algorithm. So for Buchberger's algorithm, we're going to start with a set of polynomials f1 through fk, and we would like to produce a Grosvenor basis. So what we'll do is we'll start the Grosvenor basis with those elements, f1 through fk. And we'll keep track of now all of the pairs between elements in our current generating set. So here P is storing the pairs of polynomials that we're going to produce S pairs out of. Now as long as there are pairs remaining, as long as there are things that we haven't checked, we're going to grab one of those pairs, remove it from the pair set, and perform polynomial long division to get out a remainder. If that remainder is 0, we've checked the pair, it's done, we leave it, and we never see it again, and we're happy. If the remainder is not 0 though, we have discovered something that we have to handle, we have to deal with. And an easy way to deal with that thing is just to add it into the generating set. The remainder certainly is an element of the ideal, and it's an element of the ideal that if I put it in the generating set, when I divide now by this new generating set, in exactly this step I'll be able to reduce the thing to 0. So of course as soon as I add something into the generating set, into G, I need to add a bunch more pairs into P, and these are new pairs that I have to check. This is going to repeat until the pair set is empty and I actually do have a Grosvenor basis. You might be worried, why is this thing ever going to terminate? And this is a reasonable worry. The thing to look at here, the thing that saves you, as it generally saves you in computer algebra, is no linearity of the polynomial ring. So if you look at the lead terms of G, the lead terms of our current basis, that ideal is going to get strictly bigger when I add in a non-zero remainder to the generating set. I can't make ideals strictly bigger forever, so eventually this will have to stop, and I will have a Grosvenor basis. Of course, that's not a great finiteness condition. It gives me no actual bounds. It just says it's going to stop eventually. And in practice, this thing can go for a very, very, very long time. So here's a quick example. Let's start with our original ideal, x squared minus y cubed and xy squared plus x. So the way we're going to perform Buchberger, we're going to initialize our basis to be just those first two generators, and we're going to initialize the pair set to be the pair between those generators. Now we grab something off the pair set. There's only one thing, so we have to grab that one thing. We compute the S polynomial and reduce it. We get out exactly what we saw before, this negative y to the fifth minus y cubed. That's a non-zero thing, so I add it to the generating set. I now have 3 things in the generating set. But now I also have to update the pair set to include the pairs with that new generator. So I have 2 new pairs. I grab one of them, doesn't matter which, and I compute now the S polynomial of this new pair, which does in fact reduce to 0. I don't have to do anything, it reduced to 0. I select the other pair, compute the S polynomial, it also reduces to 0, so I don't have to do anything. And the pair set is now empty, which means I can return the actual Grosvenor basis. So we were almost there. Our original generating set had 2 things in it. We actually needed just this one extra thing, and then we were done.
While G is not yet Grosvenor, so your reduction is not unique, right?
Yes, definitely true.
And so you might do unnecessary polynomials to G.
Yes. So the Grosvenor basis, so a Grosvenor basis is not a unique thing. A reduced Grosvenor basis is unique. But the actual Grosvenor basis coming out of this might have 5,000 elements, even though a reduced Grosvenor basis only has maybe 15 elements or something. So yeah, there's lots of extra things that you can add.
Just put another loop in there to just clean it up.
Right, yeah. So at the end of Buchberger, you typically will have like a minimalization and inner reduction step, where you take the Grosvenor basis you have and produce a reduced Grosvenor basis. Just like in linear algebra, you have echelon form, and then you go to reduced echelon form. Okay, so there's a variety of tweaks and tricks and additional things we should add to this if we actually wanted to implement Buchberger's algorithm. But the one tweak that I wanted to talk about, sort of ignoring the others, is this select step. So I didn't tell you at all how to select pairs out of the pair set. I didn't really mention it. And it doesn't matter for correctness. You can select whatever pair you like. This thing will terminate. You will get out a Grosvenor basis. But it does actually make a huge difference for how fast this algorithm runs. Because you might do, as you said, lots of additional extra steps, generate all sorts of additional Grosvenor basis elements that weren't actually necessary for the reduced Grosvenor basis if you select pairs in the wrong way. So how should you select pairs? It seems reasonable to select kind of small things first. Right? You're doing some kind of reduction algorithm. Let's kind of pick the small things first. If we think about, Euclidean algorithm or LLL or other types of reduction algorithms. But what does small mean? There's lots of definitions you could give. I'll give you 4. First says, pick the first pairs you saw. Essentially, put the pairs on a queue and grab them off a queue. So another way to say this, among pairs with minimal j, pick the pair with smallest I. Essentially, older pairs that showed up later in the algorithm, you're going to think of them as bigger and more complicated and messier, and do them last. The other selection strategies look at the lead terms. So degree is going to look at the LCM of the lead terms of the 2 polynomials in that pair, and it's just going to pick things with smallest degree. Now, of course, you may need to break ties somehow, but maybe you break ties with first or something. Normal looks at the LCM, and instead of just looking at the degree, it actually looks in the monomial order which thing is smallest. Again, maybe there's ties, which you'd have to break some other way, but this is the general idea. Pick things smallest in the monomial order. Sugar is the funniest one. Sugar's idea is that this tends to work better in the homogeneous case. And so it would really be nice if I had a inhomogeneous ideal to actually do things in a homogeneous ideal. But of course, I don't actually want to compute a Grosvenor basis of the homogeneous ideal because I have to compute extra stuff. Essentially, I have some kind of component in infinity that I'm computing information about that I don't actually care about. So Sugar says, let's pretend everything was homogeneous. Let's keep track of sort of what everything would have been if this was a homogeneous ideal. And let's use that, the degree in this homogeneous kind of pseudo-ideal, to make pairs choices, but actually do all the computation in the original ideal. Anyway, these 4 are kind of standard choices. There are other things you could think of, but let's look at just these 4. What I have for you now is just a table with a bunch of numbers in it. These are standard benchmarking examples, just a sort of mix of them. None of them are particularly hard benchmarking examples. They're just to get an idea of what these numbers look like. And in the table, I've written down how many S-pair reductions it took to produce a Grosvenor basis following each one of these strategies. Now on the far right, I have random. I did, for a couple of these, just do like 5 to 10 runs with random selection, choosing a pair randomly from the pair set. Then I just averaged them to get those numbers. They're probably not great measures of actual what random performance looks like, but they give you some idea. And for the ones where I didn't put a number for random, I tried this, running it for an hour or 2, and it just never finished. So random selection tends to be, as you might expect, pretty bad. The 4 selection strategies we see in front of us are reasonably good. Is one of them obviously better than the others, though? Or is one of them obviously worse than the others?
Could you explain why smaller numbers are better?
This is the number of S-pair reductions you did. So I would like to do fewer S-pair, like the number of times you went through the while loop.
Yeah, but maybe
maybe one of those S-pairs was really, really expensive.
Yeah.
Yes, absolutely, I agree. So this is a very rough measure of how much time you spent.
It's a measure. Okay.
Yeah, but you could, if you wanted to, sort of compute how many polynomial subtractions did you do, or how many monomial additions did you do. Even like adding big polynomials is more expensive than adding small polynomials. Yeah. So certainly there are more sophisticated ways to measure this.
So what is sugar again?
Sugar so your starting ideal, your starting generators, think about what their degree would be if you homogenized. So that's slightly different maybe from their actual degree, especially in an order like Lex. And then as you go through the algorithm, as you perform additions and subtractions and multiplications, keep track of what this sugar degree would be, what the homogeneous degree would be of all the intermediate results, but actually compute with the real polynomials. And then when you're selecting pairs, don't look at what their degree is in the real, actual polynomials. Look for what their degree is if they were homogeneous.
Always referencing to the original
Always reference
set.
the original set, yeah. So propagate the original set forward, as if you were doing this in homogeneous. It's as if you homogenize the ideal, and we're now computing with it. But I don't actually want to deal with anything with the extra variable. Instead, I'm just going to kind of keep track of what the degrees were.
And
No worries.
and what's on? So the names of examples.
Yeah.
Okay, so they refer to some standard examples. Are these artificially constructed benchmarks, or do they actually come from any kind of real system of equations people want to solve?
I think these two, so cyclic is cyclic roots. I could write down what cyclic is. It looks like, I mean, in three variables you have x plus y plus z, and xy plus xz plus yz, and xyz minus 1.
Yeah, so in other words...
So this is like a standard sort of crypto-ish problem. Katsura, I think, comes from physics. I think there's a particular ideal in physics. Echo, I think, stands for economics. I think there's an economics paper where this ideal is defined. Raymer and Noon, I'm not sure. I think those are just authors of particular. So yeah, I mean, some of these are somewhat artificial.
Mixture of artificial and actual.
But typically what would happen is someone would run into some problem. They had some particular ideal they wanted to compute with, and they broke Macaulay 2 trying to compute it. And so they, complained about it, and then it gets put into some database as a particularly hard ideal to compute. So, I mean, they're not like explicitly designed to be hard. I don't think people have gone out and explicitly tried to design. Well, I mean, some of these examples are, but not these particular ones.
So, just back to sugar again. So, with every polynomial, every pair, you have an integer next to it.
Yes.
That's all. That's enough information for you to figure out which is the optimal.
I don't know what you mean optimal. It's just a selection strategy.
Yeah. What is selection strategy?
So yeah, so look at the sugar degree. If you have to break ties, maybe you're going to break ties with normal selection or something.
Right. But you just need that extra integer.
Right. So you're just keeping around inside
for every pair. For every pair, you have 2 extra.
Yeah. So it's easy to implement this. You just have like polynomial comma integer, and then you write down all of what the rules would be, and just keep track of this extra integer, which is this pseudo degree.
Well, this is the regularity degree, right? This can go at single exponential.
I'm not actually sure, but maybe, yes.
Right. But do you know how high they grow?
How high the degrees go?
Yeah.
I mean, I know that, so Buchberger's algorithm is double exponential in the degree. And there are like sharp examples. There are examples that hit this bound.
It's polynomial in the degree.
Double exponential in the number of variables, sorry. It is polynomial in the degree. Is that true?
Yeah, it's like d to the 2 to the
n, right? Yes, yes.
So n isn't, so it's double exponential up there. But degree.
But the degree, yes, it's only polynomial. Yeah, I'm not sure on the actual numbers here for sugar. Okay. Other questions? I think we've reached the end of part 1. I think part 1, I just wanted to tell you about Grosvenor bases. I wanted to show that there are these special generating sets, special sets of polynomials that have nice computational properties. I showed you just one example, right? Computing whether a particular element is in the ideal. But there's lots and lots of different things. If you want to intersect ideals, if you want to compute Hilbert functions, if you want to do quotients or saturations or whatever. If you want to do computer algebra, you need to be able to compute Grosvenor bases. I showed you Buchberger's algorithm and basically how it works by adding pairs, or by repeatedly choosing pairs and adding them to the generating set after reduction. And then we talked a little bit about selection strategies and pointed out that this can make a big difference in efficiency, but that it's not really the case that we know of one selection strategy that's optimal. Certainly we could never prove anything like that. And different selection strategies in different cases can be better or worse. It's hard to tell what is a good selection strategy. So that's the question we should be leaving section 1 with. Are there any other questions that you guys have? Okay, let's go on. So part 2 is reinforcement learning. This is completely independent from part 1, although do remember part 1, because we will come back to it. Reinforcement learning, I think a decent definition, it tries to understand and optimize goal-directed behavior driven by interaction with the world. Now, that is an incredibly vague and open-ended definition, but that's, I think, appropriate. Reinforcement learning is a very widely applicable sort of problem statement and idea. And so it shows up in economics, it shows up in game theory, it shows up in machine learning, it shows up in optimal control theory, it shows up all over the place. Many particular examples can be expressed as reinforcement learning problems. Probably the most famous are games. As I kind of mentioned in the beginning, AlphaGo was a Go playing agent that was trained with reinforcement learning ideas and that could play Go better than any human. There's been a variety of other games like backgammon and chess, and even currently StarCraft. I think DeepMind is working on a StarCraft agent to play StarCraft better than people. And reinforcement learning has been very successful in playing these games really, really well. But there's also things like flying helicopters, like controlling power stations, like managing financial portfolios, or just looking at a batch of different research projects and allocating resources, money, time, scientists to these particular research projects. So what is it that kind of brings all these together? What are the particular sort of features of this problem? One thing is that reinforcement learning is typically thought of as some type of machine learning, right? But if you go and ask someone what machine learning is, the standard examples they'll give you are supervised learning problems. You have, maybe you have a bunch of pictures and you want to determine if they contain cats or something. A very important problem. And so you get a data set of 100,000 pictures from the internet and you label them whether they contain a cat or not. And then you take this input, the pictures, and this output, the label, and you train models to fit the input to the output. This is standard kind of supervised learning. Here, when you're playing chess or something, or when you're driving a car, you don't have someone telling you exactly what to do. You don't have a supervisor that explicitly says, when you see this situation, make this choice. Instead, you have to kind of try different things, see what the result is, and determine from the results you see whether that was a good choice or not, which is a very different problem. Additionally, the rewards you get in a reinforcement learning problem can happen far in the future. So if you're playing chess, you really care about winning, but winning is maybe 80 moves away. And after you perform those 80 moves, it can be hard to look back and figure out which particular move was the move that resulted in you winning, or which particular move was a good move or a bad move. So to make this a bit more precise, now that we're sort of thinking about what a reinforcement learning problem is, I'm going to express these problems as the interaction of an agent and an environment over kind of discrete time steps. And this might be an infinite series of time steps, it might be a finite series of time steps. What's going to happen is the environment at time step t is going to give the agent a state, some representation of what the world looks like. I'll call that S sub t. And then the agent is going to look at that state and it's going to have to make a decision about what to do. It's going to choose an action that I'll call A sub t, and it'll pass that back to the environment. The environment sees that action and it updates the state. The world changes because of that action. And after passing back that state, it also passes back a small instantaneous piece of reward. So the environment is then passing back states and rewards, the agent is choosing actions, and this repeats again and again and again and again. The agent in this game would like to accumulate as much reward as it can. And that is then the goal of reinforcement learning. In this particular problem, can we figure out how the agent can act in order to accumulate as much reward as possible? So to make this a little bit more precise, even more precise, we need to precisely define what an agent and what an environment is. So environments are typically modeled as Markov decision processes. So the name at least should remind you of a Markov chain, and it is sort of like a Markov chain. So we have a collection of states, I'll call them S, and we have transition dynamics between those states. So from states, we have probability distributions on the next states we're going to go to in the next time step. The difference is that along with the states, the transition dynamics also depend upon what action we choose in that particular state. And along with the next state that we go to, we get a piece of reward, a tiny little r. So this kind of horrendous looking formula, it's a function of 4 variables, s prime, r, s, and a. It really is just a normal function that returns a probability. I'm drawing that bar in between because it's really a conditional kind of probability distribution. That given some particular s and a, what is the probability that the next state is s prime and the reward you get in between is little r. So an environment implements this Markov decision process by computing this probability for the current state and the current action that the agent chose, and then sampling from the probability distribution to return the next state and the next reward. So to think about this, let's say chess, standard reinforcement learning problem. What is the state? Well, it's the positions of all the pieces on the board. So there is a finite set of states, which is all the kind of valid positions of pieces on the board. An action. Maybe we're playing white, and a valid action would be a valid move that we could play in a particular state. So the set of actions does change depending on which state we're in. That's very annoying for implementation and writing these things down, but it's totally fine for the theory. Then when you choose an action, when you make a play in chess, the environment updates by performing the other player's play. So if we're playing white and we make a move, the update is then going to be black's move against us. And there's some probability distribution on what black is going to play. The reward here is 1 if we immediately win, if we just won the game and it's 0 otherwise. Now you might complain about this, this is only rewarding you when you win the game, immediately when you win the game. You could kind of tweak this and say that there should be kind of an intermediate reward when you take an opponent's piece or something, or you get into some really good position. And there are people who worry about this, designing precise reward functions, but you have to be careful. Right? When playing chess, you want to win the game. You don't care about taking opponent's pieces. And so really the reward that we're interested in is this reward. And maximizing our reward then, or maximizing the return, is trying to maximize the probability that we win. Here's Carpol, is just another example. It's a standard kind of baby example. Have people run into Carpol before? You can see people have actually built these things. They're kind of fun. But we have, what?
What is this?
What is it? So it's a cart that is on a 1D track. It's in black. This cart can move to the left or to the right. Balanced on top of the cart is a pole, just like you might balance, I don't know, a broomstick or something on your hand. At the beginning of the game, the pole is slightly perturbed, so it's about to fall. And then, over discrete time steps, your actions are pushing the cart to the left or pushing the cart to the right. And as long as the pole is upright, I think between maybe like Megan's 15 to 15 degrees or something like this, you get a reward of 1. Otherwise, the game ends and you get no more reward. So here the state is the position and velocity of the cart and the pole, is kind of the description of the state of this system. Our actions are pushing left or right. We get 1 for every transition the pole is still upright, so we'd like to kind of push this thing left and right to balance it for as long as we can. Okay, so that's an environment, a Markov decision process. The other thing we want to make precise is an agent, which has to make decisions when looking at states. So a policy, which I'll denote with pi, is another function that returns a probability. This policy takes in an action and a state, and it returns the probability that the next action is A, given that the current state is S. So again, I write it down like this, pi of AS with a bar in between, just to remind myself that this is a conditional probability. It's really just a function of 2 variables. But the way an agent would actually implement a policy, the way it would follow a policy, is that it would look at its current state, it would compute pi of S for all of the actions. This would then be a probability distribution on the actions, and sampling from that probability distribution would return the next action that the agent would play. So in Carpol, for example, you could write down a policy that just always pushes to the left. That regardless of the state, it just gives 100% probability of pushing to the left and 0 to push to the right. You could also do something that just randomly, for any state, it gives 50% of pushing left, 50% of pushing right. You could come up with some crazier thing, right? Like if the pole's tipping to the left, maybe give a higher probability to push to the left. I don't know. You can try all sorts of things. So, more definitions. A trajectory, episode, or rollout, these are all actually the same thing. I know it is very frustrating to have 3 words mean the same thing, but I'll use them somewhat interchangeably. I'll always denote it with tau. A rollout of a policy is going to be just a sequence of states, actions, and rewards that you got when you actually followed that policy one time through the environment. So here we started in the state S0, we followed our policy to choose A0, we got the reward R1 and the new state S1, and then we kept going. Until eventually we reached a terminal state. The return of a trajectory then is just going to sum of rewards along the trajectory. It's just how much reward did I get overall. And now, after all of these definitions, enormous quantity of definitions, we can precisely state what it is that reinforcement learning is trying to solve. So given a Markov decision process, sometimes thought of as in the environment, determine a policy pi, which we think of as the agent, that maximizes this expected return of the sum of the rewards along the trajectory that you get by following policy pi. So this is somewhat strange notation underneath the E. I think you see tau sim pi. This is saying pi is some probabilistic policy. Tau is being sampled from that policy, that if you actually follow the policy pi, what is your probability of getting that? And then we're computing an expectation with those probabilities. So if you know the exact transition dynamics of the Markov decision process, if you actually know what the function p is, then this is a planning problem. You kind of know how the world works, but it's still hard to figure out what's the optimal thing to do. In the full learning problem, though, the one that really reinforcement learning is trying to solve, the dynamics of the environment, that function p is completely unknown to us, or maybe it's just infeasible for us to ever compute it. And the game then is just sampling from the environment, just interacting with this Markov decision process. Can we figure out optimal policies? Okay. Are there any questions so far? I know I threw a bunch of definitions at you that you probably haven't seen before. Are we happy with this?
Let's see what's the outcome. Then we'll
Okay. Let's keep going. So how would you solve this, right? How would you solve this? You could just start kind of guessing policies and figuring out and just running them, see which ones do better or worse. I mean, that's what we were thinking about with Carpol. I could come up with some crazy way of modeling the pole and figuring out when I should push left and right. But it's kind of hard. There are a variety of techniques for solving this problem. Reinforcement learning has all sorts of things in it. But one of these techniques, the technique that I'm going to talk about today, is policy gradient. The idea of this technique is to consider a parameterized policy function. So this is a policy function which maps states to probability distribution onto actions that depend on some parameters. And of course, everyone's favorite parameterized function in 2019 is some kind of neural network, and we will be using neural networks where the parameters are the weights on the neural network. But you can do kind of whatever you want. There's, you can have a linear function of some handcrafted features of the state, and this will all still work. So the expected return, once you have a parameterized policy, is going to be a function of the parameters, right? It's probably some horrific function that I'm never going to be able to precisely write down, but it is some function. Given some particular set of parameters, there is some expectation that I would get from following this policy.
Can you illustrate it with your the Grosvenor basis selection thing for your parameters? I mean,
what are the
suppose you can
parameters?
say, look at the 4 or 5 policies, I guess selection that you talked about, and then just say, give a probability of choosing one or the other.
Well, so all of the selection strategies we talked about were deterministic.
Right, but we can combine them using probabilistic.
We could combine, yeah, okay, so you could do like
this or
a,
that.
yeah, you could do a sort of,
Yes.
yeah, a
This
strategy
taking
where
a
you,
much smaller space, yes.
yeah, you just pick some particular strategy at random and then you follow that one, is that what you're saying? Like
Yeah, or
90% chance I pick sugar,
yeah.
10% chance I pick just normal or something.
Right, and maybe look at various, the state of the problem and then choose.
Yeah, this is actually, so this is definitely a thing you could do. I'm going to do something a little bit more complicated. But this is one thing. You could take existing strategies and just try to figure out when those existing strategies work well. And if we could decide between different strategies at different times, this could be a good way to improve our policies.
But nobody's forcing you to use the same strategy at every iteration.
No, I could, I mean, each time through the while loop, I could look at the state of the algorithm and decide, oh, this time I want to use sugar, or this time I want to use normal. I think that you're limiting yourselves a little bit, though. Like, why use sugar at all? Why not come up with some other strategy?
Oh, because that was the menu.
I mean, the menu was those 4. Why restrict yourselves to those 4? So I'm going to try to not restrict myself to those 4 in the future. But you are thinking about a reasonable thing that you could do, which is try to recognize when an existing kind of set of strategies that you have in front of you, can you recognize when one is better than the other? And I've seen this work successfully in Hilbert function computation, actually. I can point out that example later. Anyway, once we have this function of the parameters, we can think about gradient ascent. So are people familiar with gradient descent? Have you seen some ML stuff? If you're not familiar with gradient descent, I mean, you are probably familiar with multivariable calculus, right? So in multivariable calculus, you know that the gradient points in the direction of steepest increase of the particular function. So this function, j, is a function of the parameters, theta, in my policy. And so if I could compute the gradient of this function with respect to my parameters, I could move the parameters in the direction of the gradient. And that would definitely improve the policy. And so the idea would be, in gradient ascent, just to do this repeatedly. Start with any set of parameters. If I can compute the gradient, move slightly in the direction of the gradient. Now compute the gradient again, move slightly in the direction of the gradient, compute the gradient again, move slightly in the direction, and I will be traveling on a path of improving policies. You all agree?
But there should be some smoothness property on J, no?
There should be what?
It should have some kind of smoothness property.
Right, so what are the properties of J that we need here? I don't actually know quite what's going on here. J is probably some really weird, complicated function. So you're right to be very skeptical of this.
Also, for instance, in the Grosvenor basis case, which I suppose you're eventually going to apply to, It's a discrete process, I guess. So,
What do you mean discrete?
well, your parameters are not. Your parameters are just probability, so it's continuous.
And the parameters are just some weights in maybe a neural network. And the neural network is seeing a particular representation of the state of the algorithm.
Suddenly
And
you're
it's-
bringing neural networks.
We are eventually going to get neural networks. We don't need them right now.
I see.
But you're thinking about, like, how do you represent the state of the Grosvenor basis algorithm? And how do you represent the policy
Right.
that you want? And that's an important question. It's not at all obvious. And I think in particular the state side is very difficult. Like, how do you express the state of a Grosvenor basis computation so that you can feed it into some model that you can train?
Yeah, that's right.
So I'll show you one example that seems to have worked. But there's definitely, this is an open question, and there's probably lots of ideas that might work better or worse or the same. If you have any great ideas, I'd love to talk about them. Anyway, we got gradient ascent. So this, we just need to compute the gradient of j. That seems hard. J is some weird function. Luckily, we have a theorem that says if I have a parameterized policy that at least is differentiable with respect to its parameters, then the gradient of j of theta, which was the expectation of the return along trajectory sampled from pi theta, that gradient can be expressed as the expectation of this quantity. Now I could show you a quick and dirty proof of this. I could point you to a place where you can find a better proof of this. It covers the details. I don't think either one is particularly illuminating.
Right.
What is kind of illuminating is just to think about what this thing is saying. What this thing is saying is what we should do, what the change we should make in theta is going to be a sum of things, t equals 0 to t minus 1. So a sum of things along the trajectory. At each point along the trajectory, what we need to be looking at is two quantities. The quantity on the far right is the amount of reward that we got in the future. So from this time point, how much reward did we get in the future? This is a reasonably good, maybe reasonably good is too strong. This is an okay measure of how good the action we chose at that time step was. Good actions are followed by lots of rewards, just kind of by definition. So if that number is big, that was a good action. If that number is small, that was a bad action. This quantity here is the gradient of the log of the probability. So why would you do that? Well, what we need to be worried about is the fact that actions that have high probability of happening are just going to happen a lot. So I don't want to reinforce them a bunch. I don't want to constantly be increasing the chance of doing them. Actions that have low chances of happening, if they do happen, should be increased correspondingly by a larger amount. So the log does exactly what I want here. If something has low probability of happening, the gradient of the log is big. If it has a high probability of happening, the gradient of the log is small. I'm then taking that particular action and I'm increasing its probability by this quantity, this sum of RTs in the future. So increase the probability of actions proportional to how much reward I got in the future. Does this seem reasonable? You seem unconvinced.
Well, this is a new thing, so I can't say really what's...
Does it seem reasonable? I mean, it should seem somewhat reasonable, I think.
Can you give a simple illustration of this formula?
I mean, a simple illustration.
Very simple one.
I'm not sure what you mean. So if...
From the listener's point of view, from the who's trying to understand.
So suppose let's say you're playing Carpol. Carpol is an easy thing, right? So you're playing Carpol, and in the beginning of the game, you made a couple choices that kept the pole upright. But then near the end of the game, you started making some bad choices, and the pole fell over, right? So in the beginning of the game, when you're making good choices, there's lots of future reward in front of you, right? And that's how you know they're good choices. Whereas near the end of the game, when you started mistaking and doing bad things and maybe flipping the cart over or something, you didn't have much reward in the future. So certainly this quantity is going to be much higher for the actions you did in the beginning of the trajectory when you were making good choices versus actions you did in the end of the trajectory when you're making bad choices.
You don't know, right? So in advance.
You do not know in advance, right. So this thing, you have to look back at a trajectory. You have to actually interact with the environment. And then after you've interacted with the environment, you can look back at the actions you took. and decide whether they were good or bad. That is true. You're never going to be able to do this looking forward.
Yes, so it's like you want to compute a Grosvenor basis, so you that never finishes. So you actually compute it and it never finishes. After infinite amount of time, you're trying to improve it.
Yes, this is absolutely true. So you're not going to be able to do this for just one Grosvenor basis. What we're trying to design here is a general policy that works for computing lots and lots of different Grosvenor bases. And you're right that it's going to be hard to, say, train this policy on really hard Grosvenor bases to start with, because they just won't finish and we won't be able to do policy grading. To do policy grading effectively, we need to interact with the environment. We need to have a bunch of trajectories that we can look at and see what the results of our actions were.
So is it like you want to do cyclic 100 and then you'll train it on cyclic 6?
Sure, yes. Something that you can actually solve, and then after training it a bunch, if you start seeing actual good performance, then maybe you start stretching it and looking to see what it does in the examples where you can't compute it.
But you would expect it to scale to similar examples or to like any kind of examples? I don't know.
That's a good question, right? Is like outside of the examples, like you're training it on easy examples where you can actually compute lots of trajectories. After it's seen those easy examples and developed some good policy, is that policy going to hold outside of the set you trained it on? I don't know. I mean, we've seen some results that say, yes, kind of, but this is definitely something to worry about. And I don't think, I cannot tell you yes. In fact, I think that this is a major problem with what we're trying to do. Other questions about this?
Yeah.
You're confused how useful it will be? Is that what it is?
Well, I'm just generally skeptical about this whole area. So, you know, what can I say?
Oh, but it's a new area. No, give it a
Well,
shot.
even the experts, I don't think know what's good. It's, well, so what's the reason for me? I mean, you don't know the space you're working in, do you? I mean, it's that you are talking about.
So he's the expert.
Oh, maybe I have.
Let's wait until we see. So at this point, I think we have finished part two. So part two was just a general introduction to reinforcement learning. We glossed over a huge amount of material, of course, but I was just trying to show you what is reinforcement learning, what is the problem that reinforcement learning is trying to solve. And a good way to phrase this is the interaction of an agent and environment. Agents are picking actions, environments are updating state, and the agent is trying to maximize the total return it gets in a full trajectory. Policies are functions that just take in states and return probability distributions. And then policy gradient methods improve parameterized policies by moving the parameters in the direction of a gradient. And the wonderful thing about the policy gradient theorem is it tells us that we can get an approximation to the gradient simply by interacting with the environment and computing that funny expression that we were looking at just a slide ago. So if you can interact with the environment, compute a bunch of trajectories, you can approximate the gradient, then you can move your parameters in the direction of the gradient, you can interact with the environment a bunch more times, approximate the gradient again, and keep moving. And you will be improving your policy.
And is there any bounding for this number of steps that you need for this policy gradient method?
The number of steps needed for
To
what?
convert.
To converge to like an optimal?
Yeah, because I think they have like some bounds for very simple function like this contraction function,
I think, yeah, in special cases you can be more precise. In the cases we're thinking about, you cannot be precise at all. And I don't think there's any good bounds or any guarantee at all that this will even work. But if we were not, if we were not doing neural networks, if we were just doing some kind of linear function of some set of features and these had particular properties, I think you could prove things like this. I'm not totally familiar with that. Other questions?
Yes, is there any restriction that the number of action is limited or unlimited?
Oh, if there was infinite actions you're thinking about?
Yeah.
So reinforcement learning can deal with that. Typically you would return maybe a probability distribution on action, so you could return a continuous probability distribution by saying, here's the mean and here's the variance of a normal distribution. Is that the kind of thing you're worried about?
Yeah, I wonder if the number of actions is unlimited, how do you define the probability for each action?
Well, so I have to give you some kind of PDF or something that you can sample from in some way. It does work. I mean, we're not talking about it here just because we're always going to have some finite set of actions. But there are ways, yes, to generalize this to some kind of continuous space of actions that you're worried about. You convinced? You don't seem convinced. Okay. Anyway, let's get to the third part, which is the results, which is actually what we've been worried about. How do we apply this to Grosvenor basis computation? So in the first part, I just want to remind you what Buchberger's algorithm is. We saw it before. Hopefully you haven't forgotten it. And so when you look at this algorithm, do you see a reinforcement learning problem? Maybe? Kind of? Select here this function that looks at the set of pairs and has to make a decision about which pair to choose. This is kind of a policy. We could think of a policy that takes in the state of the algorithm, the state of the pair set, and gives a probability distribution on pairs, or picks a particular pair. If that is the policy, then what is the environment? Well, the environment state is going to be the current basis we have and the current pair set we're looking at. So what is in G, what are the polynomials we've generated so far in the basis, and what is in P, the set of pairs that we have remaining to process. Now the way we're going to set this up as a reinforcement learning problem is we are going to give a reward of -1 for every transition. What this means is that every transition is bad. And so an agent that is playing this game will try to end the game as quickly as possible. It will try to finish the Grosvenor basis as soon as possible, because every time it takes a step, it's getting penalized. Now there are more complicated things you could put here, like we were talking about. The number of S-pair reductions is maybe not really how much computation was spent. Maybe you should think about how many polynomial additions you did inside that S-pair reduction, and that would be the negative reward, or something similar. But for now, in the examples I'm showing you, it's just going to be -1.
Why didn't you say 0 for every transition unless the pair set is empty, you give it 1?
That would not work because the agent can just do nothing for a long time and then it gets 1 at the end. Right? I mean, I don't want to motivate the agent to solve the Grosvenor basis, just like I want to motivate an agent to win chess. I want it to do it fast.
So perhaps Chi's complaint is that maybe to do good behavior you're supposed to reward nicely rather than punish for bad behavior.
Right, we upset. Yeah, we're punishing our agent instead of giving it carrots. It's kind of mean, but it works the same way. I mean,
so actually, yeah, it's not.
So there is a difference.
Yeah, so I think you're giving it 1 when the Grosvenor basis is finished is only motivating it to finish the Grosvenor basis, but that will happen in the end eventually.
I see.
Now, if you look at reinforcement learning, you often see discounted rewards. If rewards are discounted in the future, so a reward 10 steps from now is only worth 75% of a reward right now, then this would work, your method. But for us in general, no, it wouldn't work. I mean, you're only motivating the agent to finish the Grosvenor basis, but it's going to do that regardless.
Right.
I want to do it fast. Okay, so looking at this, I wanted to give a brief talk about neural networks. I didn't really want to talk about neural networks, so I'm only giving you this slide. Are people happy with neural networks? Is that a thing?
In what sense?
Do you know how they work?
Well, I guess some don't.
Maybe we could talk very briefly. I don't want to spend too much time on this. So what I've written here up on this slide is, I think, 9 neurons expressed in gray. And so the way a neuron works is it has inputs, arrows coming into it, and outputs, arrows going out of it. And the neuron computes a value by looking at its input, taking a weighted sum, and adding a bias. So the parameters of the neuron are the particular weights it assigns to neurons that are pointing towards it, and some bias, some constant that it adds on to the end. Now, these neurons are typically put into networks. One standard way to put them in a network is to organize them in layers like this, kind of dense layers. I think this is a multi-layer perceptron, maybe, if you want to name it for it. The idea is that these first 3 values I'm going to actually input myself. This is the input to the function, x1, x2, x3. Then the hidden layer, each neuron in the hidden layer is taking a weighted sum of the input layer and adding a bias to it. Now, the individual neurons in the hidden layer could all have different weights and biases. So they all compute kind of different functions of the input. After the hidden layer has computed what its value is, That's passed forward to now the output layer. These are ordinary neurons that are taking in the hidden layer and computing a weighted sum plus a bias of those. So a nice way to think about this, the way that I often think about these dense neural networks, is that they're just doing kind of affine transformations. So if we start with here a vector x, which is just the vector whose components are x1, x2, x3, the hidden layer is just a weight matrix times x plus a bias vector, where the weight matrix and the bias vector are full of parameters. Right? Those are the parameters of the network. Those are things that we can change. After getting to the hidden layer, you do another linear transformation plus a bias to get to the output layer. Now, of course, a composition of affine transformations is still going to be an affine transformation, so I need to introduce some nonlinearity here, and this is done with activation functions. So the values that the neurons compute are not just a weighted sum plus bias, they're that weighted sum plus bias, and then they typically apply some kind of activation. I've given you a sigmoid activation here, just a very quick little plot. This sigmoid activation is a little sort of S-curve that introduces some nonlinearity. There are lots of other activations you could use. So the parameters of the neural network are the weights and the biases on all these neurons. Its input is x1, x2, x3, and its output is y1, y2. So its input is a vector in R3, its output is a vector in R2. Does this seem reasonable? Okay. So the problem, and a problem that you have already noticed already, if I want to use a neural network to model a policy, how do I take the state of Buchberger's algorithm and feed it into a network? In particular, this network, or any network, is going to expect a fixed number of inputs. What can I do? Well, here's what we thought of doing. Here's a state, a set of polynomials and a set of pairs. The way we're going to input this into a network is we're going to first fix a number of variables and fix a number of lead monomials that we're going to let the network see. Once you have fixed the number of variables and fixed the number of lead monomials, they will never change again. Your network and your agent will only ever be able to work in that number of variables, or smaller, and with that number of lead monomials. It can certainly see bigger polynomials, but it will only see that many lead monomials of those polynomials. Once those two are fixed, we can just take exponent vectors of the lead k terms of each pair and write them as rows of a matrix. So this top row, you should see, should be the first pair, 1, 2. Now 1, 2 is this polynomial, xy to the 6th plus 9y squared z to the 4th, and this polynomial, z to the 4th plus 12,012 z, or 1212z. So here I have x to the 1, y to the 6th, z to the 0, x to the 0, y squared, z to the 4th, and then the second part here, that's z to the 4th and z. The coefficients have been dropped, but the exponent vectors are there. See where these are coming in?
No.
No?
So first, I don't understand the meaning of fixing the number of variables. Just verify this.
So here I have fixed the number of variables to be 3, which means exponent vectors have 3 components.
Yeah, but you will like once you fix an example, you will know the number of variables is fixed anyway.
Right, but we are going to be training a network to work in some particular environment. What we're noticing is that, at least for this method, that environment will have to have a fixed number of variables.
So
this agent will only ever be able to work with polynomials in 10 variables.
But it can with more, but it will ignore them, or what?
It can do less. I mean, I guess we could do more, but ignore them if you'd like. That seems like a really bad idea, but
Okay.
I mean, because you're just throwing away a lot of information. Here, but so like, yeah, if it was trained with 10 variables, I could do it in 5 variables, right?
So you cannot do this for cyclic 100.
Right. The issue would be that, cyclic 100 has 100 variables in it. So I'd have to train a network that had kind of 100 variables that it could handle. And that would be a really big, complicated network. Other questions? So now what has happened, the whole point of doing this, is that this matrix, the number of rows can change. Absolutely. Across the course of the algorithm, the size of the pair set is changing, so the number of rows in this matrix is changing. But the number of columns is fixed. The number of columns is a fixed quantity. It is always going to be 2 times n times k. Because it will always, in this case, we're looking at, I think, 2 as k. and 3 as n. So we'll always have 2 polynomials, 2 lead terms, 3 variables each.
And how do, I just don't understand the entries of the...
Which row?
First row, yeah, I don't understand.
So the first row, so what we're trying to write down...
0 I understand, but then 0 to 4 I don't...
0, 2, 4 is x to the 0, y squared, z to the 4th.
Ah!
It's the second monomial, so I'm giving you 2 monomials
Why do you...
in this example.
Okay, okay.
Right, so in this example, I've picked k to be 2 and n to be 3.
Okay, well, thank you.
But you could think of k as 1, you could think of k as 10, whatever. Okay, once we have this, once we now have a representation of the state where the number of rows is changing but the number of columns is not, we still have a little bit of work to do, right? We can't feed just this matrix in because it has changed in size. But we're low battery, hopefully we'll still make it to the end of here. I have a power cord, I can get it in a second. We're almost there. Now what I'm going to do is write this down in terms of 1-by-1 convolutions. Are people familiar with convolutions? Probably not. Like what a 1-by-1 convolution is. What you should think about this doing, here is our matrix. The size, the height of the matrix is p, the number of pairs in the pair set. I'm adding on an extra dimension, that's just going to be 1. The depth of the matrix is 2 times n times k, because that was the number, the length of the exponent vectors that I concatenated together. What I'm going to do with this input is I'm going to apply a 1-by-1 convolution to it. Now, a 1-by-1 convolution in this way is just going to take a fixed kernel and apply it to each row of the matrix. So another way to think about this, if you do not like 1-by-1 convolutions, is to think about this as a dense network, just like the network I showed you before, whose input is 1 row of the matrix, goes through a couple hidden layers, and output is a single number. So what our network is going to do is it's only ever really going to look at 1 row of the matrix at a time. It's going to be a dense neural network on that ends in a single number. So it is going to output a single number at the end for each row. This number we're going to think of as a preference score. How much does the network like this row? And the way we're going to convert that preference score to a probability distribution is to apply a softmax activation at the end. Softmax just takes the numbers in this vector, which has a number for each row, it raises them each to an exponential, and then normalizes. And what comes out is a probability distribution that's used kind of standardly and in other kind of classification problems. So this particular network structure, which I admit is maybe not the greatest network structure, will be able to take in kind of arbitrary ideals and arbitrary states of Buchberger's algorithm as long as we fix a number of variables and fix the number of lead monomials that the network can see. You all agree? Okay, so just to remind you, maybe as I grab my power cord here, how policy gradient works. We're going to initialize the weights of this network completely at random. And then we're going to go through a series of epochs. And in each epoch, we're going to make a policy gradient step. The way that works is we will take our current network and we will follow it. Is there a power cord around here? One way over there. Oh, there's one, I think. So we're going to take this network and we're going to have it interact with an environment. We're going to have it look at a bunch of ideals and actually follow Buchberger's algorithm, following the choices it makes for the selection, and compute Grosvenor bases from them. Once it's finished, here I say 100 rollouts. I mean, that's a number that could be 10, it could be 1,000. It's a hyperparameter that you're going to have to tune. Once it's finished with those rollouts, though, we're going to look back at them.
So what's rollout?
Rollout is an episode or a trajectory. So it's just one ideal, the full series of steps that resulted in a Grosvenor basis. So each selection until we finally reached a Grosvenor basis.
And where does 100 come from?
100 is just a choice. It's the choice that I'm going to use for the examples. that I'm going to show you, but it could be 10, it could be 1,000. This is another kind of hyperparameter that you have to tune. It's not, has to be 100. So when you've generated these episodes, when you've generated kind of full Grosvenor basis computations for these 100 examples, you're going to look back at all the trajectories, at all of what you did and what happened afterwards. You will compute the future rewards, which is just this sum of -1s in the future for each step. We're going to add 2 tweaks to the policy gradient theorem. One is that we're going to baseline by the size of the current pair set. What this means is that we will not penalize the agent for how many pairs were in the pair set when it made its choice. So the agent is getting penalized for every S-pair reduction in the future, but if it started with 10 pairs in the pair set, it doesn't make sense to punish it for those 10 that had to happen in the future. So remove that, and we're also going to normalize these scores that we produced across the entire epoch. This just makes it nicer to pick a particular learning rate and have that learning rate work across a variety of examples and states of the algorithm. Once you've computed this quantity, which is, in expectation, the gradient, you're then just going to move your parameters, your weights of the network, in the direction that it tells you. So, to conclude this, I have 3 examples of applying this to some problems and seeing what happens. So in the first example, to spoil it a bit, we're going to see that we can essentially learn degree without telling the agent anything about how polynomials work. So, setup, we need to pick a number of variables. So I'm going to pick 3 variables. And I'm going to take things from the ring in x, y, z over my favorite finite field, and now we're in Grevlex, just because Grevlex is the standard place to be doing computations. The ideals we're going to be looking at are generated by 5 random binomials of homogeneous degree 5. What I mean by that is that I am going to look at all the monomials of degree 5 in these 3 variables. I'm going to pick 2 of them uniformly at random, and I'm going to put them into a binomial by putting the first one and then a random coefficient, a random non-zero coefficient times the second one. I've generated a random binomial, do that 5 times to generate 5 random binomials. That's the ideal. Now, unlike in other areas of machine learning, we don't have some fixed test set and train set or anything. We just have some generator that's giving us random ideals. And as we interact with them, we'll see how well we're doing by looking at what our previous epoch's performance was, and hopefully see it going up. The agent that I'm giving you right now only sees lead monomials. I've chosen k to be equal to 1, and the network has a single hidden layer of size 48, which means overall we have a pretty small number, 385 parameters. This is very small for a neural network world. Total training time here is only 15 minutes. It was much slower in the past, but as we've improved things, it's gotten much faster. This is what you should see. So, on the x-axis is the epoch. This is increasing in time to the right. In each epoch, we have 100 episodes, 100 rollouts, 100 trajectories, whatever you want to call them, 100 ideals that we computed the Grosvenor basis of. And what I'm plotting for you in, I think, light gray, is the agent's average performance on those ideals. It's essentially just the negative of how many S-pair reductions happened before a Grosvenor basis was computed. Now this bounces all over the place, it's kind of crazy, so I've also smoothed it out a little bit for you in dark black, a 10 epoch moving average of the agent's performance. Now there are a couple kind of landmarks to think about for this problem. The first is random performance down here at the bottom. This is what would happen if you just selected pairs at random, kind of how much you would average in total return. First performance up here in the middle is in orange, and then degree, normal, and sugar all have actually the exact same performance in this particular case up here in green. And so what we see is our agent starts around random performance. It very quickly spikes up to beat first, and then slowly over time is kind of getting better and better, approaching degree performance. And in fact, if you continue running this for longer than 15 minutes, if you run it for a couple hours, it will get closer and closer and closer to that green line up there at the top.
But this says that this method is not needed, right?
Right. So this should be very reassuring in that this works. Right? We have actually learned a strategy that's not just guessing randomly. But you should be unhappy because this is not better than any strategy that you know of.
Well, on the other hand, you made the computer discover human being thing, which is from the
That's right. Yeah.
Exciting.
Yeah. I mean, there were a lot of graphs that did not go up like this. before I saw this graph.
So this is for a particular set of monomials?
Particular set of binomial ideals,
Binomial ideals.
which are generated at random of degree 5, homogeneous
Right.
degree 5.
So you learn from this random set, and then you apply it to something new?
To this random set. I mean, you're just seeing how well it does on
On
kind of
itself.
random samples. Yes. So this is sort of standard reinforcement learning. You just have some random ideal generator instead of thinking about a particular train and test set.
Okay. All right. Well, sounds impressive.
So, is this thing actually learning degree, is one question you might have. And I think it is. It's very hard to interpret neural networks in general. But one thing we can look at is what are the preference scores that the network assigns to particular rows. Now those rows, I can actually compute what the degree of the LCM is. Like, I know how to do that. And so on the x-axis, I've plotted what the degree of the LCM of a set of pairs actually is. On the y-axis is the preference score the agent assigned to that pair. So before training, it's just kind of random. There's no real connection. But after training, what we see is much higher preference scores for smaller degrees than for larger degrees. So note that these preference scores are going to go into an exponential before they become probabilities, which means even tiny differences are going to be magnified. Now this thing has not totally settled onto degree, because you can see that there are things of degree 4 that it still might prefer over things of degree 3. But as you train it for longer than 15 minutes, these will become more and more split up, and it will become closer and closer to actually producing degree. Anyway, that's example 1.
And is degree the best, or
In this particular case, degree was the
did
best.
we actually know that?
It's a good question. I mean, degree is the best of the 4 strategies tried on this particular case. I don't know if you could prove it's optimal. It is homogeneous, so I don't know. I don't think you could prove it's optimal, but I wouldn't be surprised if it was. Anyway, this example showed we could kind of get close to degree. We could sort of learn a strategy that we already know is good. But as you already kind of wanted, can we beat the strategies we know? That would be the real thing. And so example 2 makes this game a little more interesting. We still have 3 variables, but now I'm going to up the degree, and I'm going to make these binomials inhomogeneous. This will introduce a little bit more interesting behavior. So the ideals are now generated by 10 random binomials of degree less than or equal to 20. The way that's going to work is that I'm going to pick uniformly at random a degree between 1 and 20 for 2 monomials. Then for each of those monomials, which I now know their degree, I'm going to pick the actual monomial uniformly at random from monomials of that degree. Then I'll pick a random coefficient and place those together into a binomial. Do this 10 times, you have a random ideal. The agent is now going to see 2 lead monomials. The wonderful thing about this is that in binomial ideals, as you perform Buchberger steps, they stay binomial. So the agent is, throughout this entire algorithm, going to see kind of the full binomial, except for its coefficient. The network now has 2 hidden layers. I've made it slightly bigger, size 48. We're still not really that big in the land of neural networks, looking at about 3,000 total parameters. And total training time now is 8 hours. This is the plot you should see. So this is definitely going up. The landmarks, again, to notice. In blue, random performance is here, which is where we start, of course. The network is randomly initialized, it's just guessing. Degree and normal are actually worse than random in this case, which is a little bit surprising, but it's not too unusual, at least in some of these examples in 3 variables. They're down here, but up here, first and sugar are kind of the best that we know in this particular set of examples, and we pretty quickly go above them, and after 8 hours of training are about 10 to 20% better in terms of the number of S-pair reductions. So we are computing the exact same Grosvenor bases these other selection strategies would compute, but we're doing it in 10 to 20% less, or fewer reductions. So this seems nice, right? This is actually improving. Now, the obvious question is, what is it doing? And the answer is, I don't really know. I can show you another graph that is kind of the degree preference like we saw before. And this agent does appear to have a pretty strong degree preference. It likes things of small degree. but it's not clear how it's kind of breaking ties. It's definitely not doing degree. I mean, degree actually has pretty bad performance in this case. So it's somehow picking up on some additional information. I don't quite know what that additional information actually is. Okay, one last example. So here I'm going to up the number of variables. Now we're in 5 variables. Of course, the real way to make Grosvenor bases hard is to increase the variables, so we're getting into a much more interesting case when we get out of 3 variables and out of 5. The ideals are going to be generated by 5 random binomials of degree less than or equal to 10. Agent still sees both monomials in the binomial. The network has 2 hidden layers, slightly bigger, so for a slightly larger set of about 5,500 parameters. Total training time here is a little over a day. And this is what we see. So here's our random landmark. It's where we kind of start. Actually, we're a little bit unlucky. We start a little below it. These are what we're trying to beat. First here, normal and sugar here, and then at the top, degree. And we are improving, right? We might continue to improve if we continue training, but this is taking a really long time. And in fact, this was cut off after 1,000 epochs in 26 hours, just because it was taking too long. And we needed to figure out, can we do this faster? So why is this taking so long? What is really the trouble? And one way to think about, or one particular problem with this, is that for this particular distribution of ideals, there are some ideals that are just harder than others. So policy grading is trying to decide how good actions are by seeing how many future reductions happened. Now, if all of the ideals took the same number of reductions kind of on random, or like on average, then this would work all the time. Because good decisions, good choices of pairs, would be followed by few pair reductions. But some ideals just have way more pair reductions that you're always going to have to do. So we need to deal with that. So just to convince you of this fact, in case you're unconvinced, here is, if you generate 10,000 random ideals from this distribution, this is what the returns look like following random selection. So there's definitely a pretty crazy left tail here. And there's a wide range of different numbers of reductions that you have to do to actually compute a Grosvenor basis. So this is going to be really hard for policy grading. Policy grading cannot tell whether the action it took was bad because it was actually a bad action, or whether it just got unlucky and had a bad ideal. Now that's random selection, which of course you maybe think is, yeah, of course it's random selection. It's going to have a lot of variance in it. But here's degree selection. Degree selection was the best choice here. And it still has a pretty wide range of returns across different ideals. One way to think about this, to justify why this should be the case to yourself, is you can actually look at what the size of the reduced Grosvenor basis is of these ideals from this particular distribution. And the size of the reduced Grosvenor basis actually has a pretty large range. So some Grosvenor bases really just are harder to compute. So the idea here, in order to make this easy for our policy grading agent, is to pre-compute, let's say, 1,000,000 ideals, and then let's bin them into maybe 50 different bins, where each bin contains ideals that have a similar number of reduced Grosvenor basis elements. What I'm thinking is that each bin is kind of a similar difficulty of ideal. And now what I'm going to do is I'm going to train the policy grading agent by having it first, at random, select a bin, then train from 100 ideals on just that bin, and then I will evaluate it on 100 random ideals. So the evaluation is the same, but the training is now binned. It trains on a particular subset of the distribution at every epoch. That subset is chosen randomly at the start of the epoch. And here's the picture you get out. So, as always, we start down here at random, but within just a few epochs, we've actually jumped all the way above degree, where we stay for 100 epochs. This is the same kind of 10 to 20% improvement we saw in the previous example, but it's now in this kind of bigger example. And again, this is actually a huge improvement. I mean, I couldn't even plot these things on the same scale, right? This was after 1,000 epochs, almost 26 hours of training. We're just barely getting to minus 325 or something. We're just barely beating first. Here, it's the exact same environment. It only takes us maybe 5 to 10 epochs to start beating everything. And I mean, certainly by 20, we're there. So this only takes a couple hours of training, maybe I think 2 or 3 hours of training. I think actually just 1 hour of training to get to 20 here. And so the overall speed of training is maybe 2 orders of magnitude faster. Anyway, that is the last of the 3 examples I wanted to show you. So these examples, what should you take away from them? First, policy gradient agents that just see these lead terms in this particular network structure, they can actually learn strategies that approximate degree selection, which is a nice kind of reassuring thing that tells us that this method is maybe not too crazy, that we can find strategies that we know are good. When policy gradient agents see full binomials, we have seen several examples where they're actually learning strategies that perform 10 to 20% fewer pair reductions than our known strategies. So they are better than kind of state of the art in this particular problem. Now, a major challenge we're facing is this high variance problem. How do we train our agents on sets of Grosvenor bases, sets of ideals that have wildly different Grosvenor bases? And that's definitely a hard problem that we're trying to address. There are other ways to address this problem, but we saw the particular example of binning making a huge improvement and suggesting that really if we want to push this further, we have to rely on these types of tricks. We can't just give it a random ideal. So that is all I have for you. I guess just to conclude where we want to push this further, where we want to go with this. Certainly bigger examples on larger networks. We're using very tiny networks at this point, so if we could get larger networks, if we could get bigger examples, larger distributions, if we could just throw more compute at this and see what kind of comes out, that would be interesting. In addition, different algorithms. So other than policy gradient, there are a variety of other techniques in reinforcement learning. There are more kind of sophisticated things, more sophisticated algorithms based on policy gradient. There's value functions, there's Monte Carlo tree search, which seems like it is particularly suited to this problem, but we haven't played around with too much. And there's also just other computer algebra algorithms where we have choices. Even this algorithm, we're looking at just the selection step in Buchberger. But you could also think about what do you use as polynomials when dividing? What do you use as the reducers? Whether you eliminate pairs or not, and other choices that you could possibly make. So that is all I have for you. If there are any questions, I'm happy to address them at this point.
So, I don't really know what's... But can one say that what you're learning is learning the statistics of the space that you're searching? Statistical properties.
Yes, I think that's true.
Yeah, you're just summarizing it in some strange way, the weights that are hidden in the
Right, yeah.
network, and then the thing is that how do you transfer it to another environment where you don't know anything in advance? That's
right.
Transference is not clear at all, right?
Right, yes. So that is something you definitely should be worried about. And so we have seen, like, in the networks that learn degree, we saw that when we moved outside of that particular environment, they still did kind of know degree. So they still did apply kind of the same degree selection to bigger ideals or different ideals. But there was some difficulty transferring into a new distribution, and you should absolutely be worried about that, whether this is just learning particular properties of the distribution we're training on, or whether it's learning an actual generalizable strategy. That's not at all clear.
So the question is, what kind of spaces are we dealing with, and what's their relation?
You mean like the spaces of ideals? Like
Yeah.
This is another very good question. Like, what are good distributions of random ideals? Really, what I would like is some set of ideals that is kind of the typical ideals that Macaulay 2 is asked to compute. Like, what are the sort of ideals that people are putting into Macaulay 2? What are the sort of ideals that come up a lot?
How do you collect that kind of information?
We could conceivably, keep track of what people put into. I mean, people have talked about this, but no, we do not keep track of what anyone is putting into Macaulay 2. But that would
use Macaulay, it actually communicates with.
No, it does not.
You're sending your polynomials to them.
It definitely does not. I believe Dan Grayson would be very upset if that ever happened. But it is that's kind of how a lot of industry reinforcement learning applications work. Google or Microsoft or whatever is keeping track of everything you do. And they can use that as training sets for algorithms and actually look at what the distribution of actual uses is and train on that. which is kind of what we want here, but is not what we're really fitting to. What do you got?
Would it be interesting, instead of big even monomial ordering, finding the strategy, so instead of this, you fix the strategy and you try to find the monomial ordering that leads to the, that allows to compute more efficiently the probabilities.
Yeah. So this is definitely another question you could try to answer. Like, pick a monomial order at the start of the algorithm. Like, look at the ideal and pick a monomial order where the Grosvenor basis computation would be fast. This would actually be kind of a supervised learning problem. If you could generate a data set of ideals and which was the best ordering for them. You could train just a supervised learning agent. I've heard people talk about this. I've never seen it actually.
There is a, I was on the thesis of a student of James Davenport. Do you know?
I don't think so.
Just using learning, but not in a certain Grosvenor basis, but for CAD, cylindrical algebraic decomposition.
I think I have actually seen like an archive paper that was talking about that.
Right.
That was choosing. Okay, maybe it's the same person.
Doing some of that. Yeah.
No, this is definitely an interesting thing to do. Yeah. I think this is much more general, right? This is much more like there's this huge possible set of strategies trying to find a particular strategy. What you're talking about would actually be a little bit more approachable, but would still be a really
monomial ordering, there's a huge.
There are a huge number, but
Yeah, uncountably many.
So a lot.
There's a lot.
You can represent all this orderings by weight matrix.
Right. Yeah, and then just
The space is huge.
So you see, so apart from collecting usage data, how would you see incorporating this into a computer algebra system?
Well, once we've trained something with these particular distributions, we could certainly incorporate it into a computer algebra system. We could.
Well, but for it will be for.
But you'd be worried about, like, does it generalize outside of these particular examples?
And not just generalize, but does it give an advantage?
Right. Yeah. No. That's certainly the case. But when people looked at developing sugar, they were comparing just a couple of benchmarking examples. So we could do the same thing here. Once we've kind of settled on a particular network that we think is good, we could try to implement that particular network and then run it on some of these benchmarking examples, see what it does. And it would be the same kind of justification that we have for why sugar is a good strategy.
Wait, but you have to use your network now to apply to an arbitrary basis computation.
Right. So
how do you do that? How do you map it into your neural network that you've trained?
Well, one of the issues is that this neural network has some fixed number of variables, which is going to be hard to change. The way we set this up, we can't change it. So we've thought about different neural network structures that would address this, but you'd have to come up with some other neural network structure if you wanted
Are there
to
such network structures out there?
Well, there's things like recurrent networks that can kind of take in a polynomial of arbitrary length or take in a set of variables of arbitrary length. These could be applied. We haven't tried too hard. But yeah, that's a hard question. But you could certainly write this down for if you're in 5 variables, if you're in 10 variables. We could take our particular network structure and write down in Macaulay 2 what the preference scores are, what the function that produces preference scores is, and then we just sort by those.
More questions? All right, thank you.